These are solutions to recitation activity 5. So how many moles of ions are present in 75 milliliters of 1.25 mole per liter K2SO4? This could have been also written as 1.25 capital M K2SO4, said out loud, 1.25 molar K2SO4. That's moles per liter. So K2SO4 in solution, this is a water-soluble compound. It's an ionic compound, so therefore it's a strong electrolyte. So it's really 2K plus ions plus an SO4 2 minus. And so we're getting 3 moles of ions per 1 mole of K2SO4. So the number of moles of ions we get here would be equal to, let's take 75 milliliters, 1,000 milliliters is 1 liter. That's our solution, times 1.25 moles of K2SO4 per liter of that solution. And then 1 mole of K2SO4 gives us 3 moles total of ions in the solution. So my ion number of moles would be 75 divided by 1,000 times 1.25 times 3 would be 0.28. Or excuse me, 0.28 moles of ions. And so we could think of this moles here, 0.075, the 75 divided by 1,000 times 1.25, I have 0.094 moles of the sulfate ion, and then I would have double that, 0.18 moles of K plus. Add those together, we get 0.28. So that's the moles of ions total in the solution. So again, we're just getting twice as much K plus as K2SO4 because we have 2 moles of K plus that fall off of K2SO4, and then just 1 sulfate ion per mole of K2SO4. Next question. We have 150 mils of that concentration of K2SO4 placed in a 1 liter flask. Flask is then filled with water to the 1.00 liter mark. What is the concentration of the solution? So I'm terrible at art, so this is a terribly drawn volumetric flask. But the idea is this flask, when you fill it in this line with a nice meniscus, would fill precisely to 1.000 liters. And so we just put some of the, put 150 mils of the K2SO4, then we fill the rest of the solution with water. And so this is a dilution. We can either use the dilution equation or just think about molarity and the final volume. Let me think about the molarity problem. Let me solve for the moles of K2SO4 initially in the solution here. So I have 0.1500 liters of that solution times 1.25 moles of K2SO4 per liter. And so that gives me 0.15 times 1.25. That's 0.188 moles of K2SO4 in that solution. And then we're just changing the total volume from 150 up to a total volume of 1 liter. So we just need to divide this by 1.00 liters. And so that's going to give me 0.188 moles per liter. Now, an alternate approach would have been to use the dilution equation, MIVI equals MFVF. If we want to use this equation, we can just plug in the initial molarity, the initial volume, and then our final volume. Just match these units up so they're both in liters or milliliters. So I'll keep it as 1.25 times 0.15 divided by 1 gives me my answer of 0.188 molar. So equations work too, but we just have to know how to use them. Question 3, how much KHCO3 in grams must be added to completely neutralize to fully react with this quantity of acid? We have the full reaction here where every 1 mole of H2SO4 that's present has to have 2 moles of the potassium hydrogen carbonate added to it to fully neutralize it. So this just means to completely neutralize just means to fully react. So that's a synonym would be to fully react or to fully neutralize the acid, how much of this base has to be added. And so the way we can work this out would be to take the number of grams that we're looking for of KHCO3. I'm going to take my moles of H2SO4 I can calculate from the initial volume. So I'm going to go in liters, and of course this is moles per liter, so that's why I'm converting this to liters. And so times 1.0 moles of H2SO4 per liter of that solution. And then for every 1 mole of H2SO4 that's present, I have to add 2 moles of KHCO3. So it's looking like I have to add half a mole of KHCO3, because that's 0.25 times 1 times 2 is half a mole. And then the molar mass is about 100 grams per mole, so I'm going to have to add about 50 grams. So when I go 1 mole of KHCO3 to 100.1 grams, this is going to work out when we do this math to be 50.0 grams, and I'll just double check. So 0.25 times 2 times 100.1 is 50.0. Now, from the results of a titration, 25 mils of iron 2 nitrate, FeNO32, the sample of iron nitrate completely reacted with 40.15 milliliters of this KMNO4 solution, presumably an excess acid. So this here is what we're trying to determine the concentration of. What's the molarity of the sample of FeNO32? So we presumably have enough of this. We have so much of the KMNO4 that had to be added, so we should be able to figure out the moles of FeNO32 that were initially present. And so the way I can solve this problem here is let's try to figure out the number of moles of FeNO32 that had to initially be present from the fact that we had to add 0.04015 liters of 0.0175 moles of KMNO4 per liter of that solution. And then my conversion factor here is that for every 1 mole of KMNO4 that we had to add indicated that there were 5 moles of FeNO32 initially present. So do the math there, 0.04015 times 0.0175 times 5 means that there were initially in that solution 0.00351 moles of iron 2 nitrate initially present. And so if we want to work out the concentration of that solution, in that 25 mil portion that we were titrating to determine its concentration, I just take that number of moles and divide by the volume. So the idea is we have this 25 mil portion of a solution of iron nitrate that we want to know its concentration before the reaction takes place. So we figure out how much of the other reactants needed to fully react with it. We must have had some color change that went off to indicate the end point of this reaction. That's the whole point of a titration. And so we don't have to even understand how this is done in the lab, but just from the math of how much of the KMNO4 it took to fully react with the iron nitrate tells us how many moles iron nitrate had to be present, so we can work out its concentration. And so we'll divide the number of moles there by 0.025 liters, and that works out to 0.141 molar. So the answer D. Which compound does fluorine have an oxidation number of 0? Let's just work out all the oxidation numbers here. So in KF, potassium can only be a plus, so fluorine's a minus. That's an ionic compound. HF's a molecular compound, but molecular compounds with hydrogen, hydrogen's plus, fluorine's always minus, so plus minus as well for HF. The difference here is that we really have an ionic compound here, but in HF, this is really some sort of molecular compound. The idea is we have partial positive, partial negative. You're getting the idea that H is the positive atom, fluorine's a negative atom. We'll talk about this more in chapter 8 in terms of the actual bonding models and how we're getting these charges. But ClF3, so for the idea here being that the charge, the oxidation number is assigned, or really just so we can get the signs right on these charges. So we get the positive sign right, the negative sign right for the H and the F. Cl and F3, same basic idea. Fluorine's charge in compound's always going to be -1, so chlorine has to adjust accordingly to +3. And then F2, in an elemental form, all the oxidation numbers are 0. So the one with fluorine of 0 is answer D. Number 6, which compound below has an O atom with an oxidation number of -1? So let's just work all these out. This is, of course, an ionic compound. Potassium is always plus, so +2. This is potassium oxide by nomenclature standards, so that's oxide ion. Oxide's O-2. LiO2, lithium's always a plus, so O2, the collection have to have an oxidation number of -1, so each O is -0.5. And so we're not going to be answer B. I guess I forgot to unbold answer C, so we know it's going to be C. But H2O2 works because hydrogen in molecular compounds has to be +1. This is a molecular compound, only non-metallic elements. So the collection of 2 oxygens is -2, so -1 per O. So answer C is going to work out. TiO2 might trick us a little bit. Is this a peroxide compound or a superoxide? Well, those only form with alkali metals, alkaline metals, and we see here hydrogen, not with titanium. So this is just regular oxide ion, 2 of them, -4, +4 titanium. And so this is titanium 4 oxide, if you think about its name from chapter 2. So oxides are oxygen with a -2 oxidation number. Which process below absorbs heat and is endothermic? The combustion of natural gases, this releases heat. You can see the flame when those reactions take place, so this releases heat. The boiling of water, so liquid water, in order to vaporize, has to absorb heat. So this is an endothermic process. So it has to absorb heat to boil. So we have to absorb heat in order for any substance to go from its liquid to gaseous state. So only two is a process that absorbs heat of those 2 choices. Number 8, a chemical reaction that warms up its surroundings is said to be, that's exothermic. Sometimes we get these backwards, but exothermic means the reaction releases heat. That would be Q reaction. We often think of this as the system. So the system and the reaction are the same thing, and then this would be less than 0. So Q reaction less than 0 is the reaction where the reaction's losing heat. The reaction loses heat, so you have, imagine an A goes to B, so your reactants are up here in terms of their relative heat, and your products are below, and so heat's being released. Where does it go? Where does the heat go? The heat goes in the surroundings. So the Q reaction is the negative Q of the surroundings. So if the reaction has a sign of negative for its heat change, then the surroundings has a positive heat sign. So the temperature of the surroundings in this example here, they're greater than 0 for a reaction that's releasing heat. So a reaction that releases heat, where does it go? It goes to the surroundings. The surroundings gains the heat in this example. So exothermic reactions release heat. The heat goes to the surroundings. The temperature increases, and then the sign that delta H is our state function for the molar quantity of a substance undergoing a change. So the delta H of this process would also be negative. So delta H falls off of the Q reaction. It's really the Q reaction for a specific quantity of the reaction. But our delta H will have the sign of negative, just like Q reaction. So exothermic negative here for delta H and for the heat change of the reaction. Question 9. The complete combustion of ethanol proceeds as indicated below. How much heat is absorbed or released when a quarter of a mole, 0.250 moles of ethanol reacts or combusts? Okay, so the reaction is negative and it's delta H. That means, just like from the previous example, that this is exothermic. Heat is released. So how much heat is released? Well, let's calculate our Q reaction. I tend to think of the Q reaction as for a specific quantity of reaction. Delta H is for kind of a reaction where you have it written and the coefficients are understood to be moles. So you have 1 mole of ethanol plus 3 moles of O2, forming 2 moles of CO2 and 3 moles of water. That this reaction as written has the delta H of minus 55.5 kJs. And so the way I would think of this here is that the Q reaction would, for a quarter mole, would be 0.250 moles of ethanol. And then the coefficient would be, I have minus 555 kJs, and that's per 1 mole of C2H5 hydroxide. So I have to kind of inspect the coefficient here and include that coefficient here. And so 0.25 times negative 555 is minus 139. And so we have 139 kilojoules being released. So 139 kilojoules is released by this reaction when it takes place. Now, in my head, I'm thinking I could change this, but maybe your TAs can mention that, well, how does this problem change if we said, well, what if 0.25 moles of oxygen reacts with the required amount of ethanol? So let's say you have the same reaction take place where 0.5 moles of O2 fully reacts. Then how much heat is released by this reaction? Our Q reaction in this case would be if we have half a mole of O2, let's call it 0.50 moles. So let's call this 0.5, just get an extra sig fig on this. And let's even call it 0.250 moles. So what if we do a different problem here? Like a second question would be, what if you took a quarter mole of oxygen that fully reacts with the required amount of ethanol? And so we're going to take the 0.25 moles of ethanol, or excuse me, the 0.25 moles of O2. And then the difference here, and this is really sometimes an easy mistake to make, is that it's minus 555 kJs per 3 moles of O2, because the coefficient in that reaction is 3 for O2. And so for the quarter mole of O2 reacting, you could think it's going to react with much less than a quarter mole. It's going to react with a third of ethanol. So the heat that's released is going to be of less magnitude. So 0.25 times negative 555 divided by 3 is only going to be minus 46. So Q reaction's negative 46 kJs. So we have 46 kilojoules being released. So less heat's released when a quarter mole of O2 reacts because the coefficient of 3 in front of O2 in the reaction means less of the reaction is taking place. So we have an enthalpy of water water solid to water liquid is plus 6.01 kJs per mole. So 1 mole of ice to 1 mole of liquid water plus 6.01 kJs. What is the enthalpy of the below reaction? So what happens here when these are 2? Well, again, we're assuming these are 2 moles. So the idea is that it's 6.01 kJs per mole of water. And if you have 2 moles of water present in this reaction, then we need to double the magnitude of delta H. So this would be 12.01 kJs. So the sign's gonna also, something I almost missed, is that we flipped the reaction too. So now we have water liquid going to water solid. Now, ice has to absorb heat to melt. That's why the sign's positive. So this is an endothermic process because ice has to absorb heat. You have to warm it up in order for it to melt. Now, in order for liquid to freeze, you got to lower the temperature, take heat away. This becomes an exothermic process. If you flip a reaction, you got to flip the sign. That comes in the first law of thermodynamics. So if water solid to liquid is plus 6.01, if you have water liquid to water solid, and you just flip the sign, delta H here would be negative 6.01 kJs, double the coefficients, then you double the magnitude of the delta H. So this delta H here is going to be minus 12.0 kJs. Which statement is true for ammonium nitrate dissolving in water where our delta H is positive? So this is an endothermic reaction, meaning heat has to be absorbed for this reaction to take place. So if you put this solid compound into water, and it dissolves and ionizes as it should because that's a water-soluble compound. So we know the reaction takes place. It's just going to take place in an endothermic reaction where heat's going to be absorbed from the solution. So the water temperature, the solution temperature is going to drop. So the solution drops in temperature because the reaction absorbs some of its heat. Answer B would be true. The solution temperature doesn't drop because the reaction released heat. The reaction doesn't release heat. Exothermic reactions, negative delta H reactions release heat. This reaction absorbs heat. Sometimes we get confused and think, well, the reaction absorbed heat, so it had to increase in temperature. But no, that's not how temperature is related to heat here. Think of the temperature of the water. Water is the surroundings of this reaction. It's not the reaction itself. So the water that surrounds the reaction lost its heat because the reaction that took place absorbed the heat. So you can't really, it's hard to think about how you would put a thermometer on the reaction itself. Like we're not saying the thermometer is measuring the temperature of the reaction. We're saying measure the temperature of what the reaction's in contact with. What the reaction's in contact with is the water, the surroundings temperature is going to drop. So it just because the Q surroundings, the heat change of the surroundings versus the heat of the reaction, that the reaction here is increasing in its heat, the surroundings has to be decreasing. And so we have this relationship that the heat of the reaction is the opposite of the surroundings. Again, if the reaction increases its heat, the surroundings has to lose heat. This means the temperature of the surroundings must drop. Okay? And so that'll lead to answer B. Last question is if we put iron or aluminum into water. So we have would iron or aluminum be equal masses at 100 degrees C. So we've taken a mass of iron or a mass of aluminum where we have given specific heats. Note that the specific heat of aluminum is higher. So to get these metals up to 100 degrees C, presumably it would have taken the aluminum longer to increase its temperature. So if you imagine just putting these metals in like a test tube, put the test tube into water and you're seeing how long, maybe you have a little thermometer probe into the metal, it would have taken aluminum longer to heat up because it had to absorb more heat because its specific heat's higher. It means it has to absorb more heat for the same amount of mass to increase its temperature. And so then we're going to put those metals, we're going to imagine you take your test tube of just the metal and you like pour each of them into two different beakers of water where the beakers have the same amount of water. Which water, and the water in those beakers is initially at room temperature. So you have, beaker 1, beaker 2, and you put the iron into the one, and you put the aluminum into the other. And so these are hot. The heat is going to be lost into the water. So heat's going to evolve out of these metals into the water, and the water temperature is going to increase. So the temperature of the water is going to increase. And so the temperature of the water is certainly not going to decrease. So two choices are completely baloney. So you're not going to put a hot object into room temperature water and have the water temperature drop. That would be crazy. Okay? And so the aluminum had absorbed more heat, has more heat to give off. So the aluminum has more heat to give off. It's going to increase the temperature more. So the aluminum is going to cause water to have a greater temperature increase because it absorbed more heat, has more heat to lose. So you can think Q is equal to MCS delta T. The heat that it had absorbed is just simply greater. You could also think of this as if the specific heat of water is a lot higher than these quantities, that if you could take 10 grams of aluminum, 10 grams of iron, or 10 grams of water. 10 grams of water is going to heat the water up if it's at 100 degrees too. 10 grams of boiling water, poured into room temperature water, will increase that water temperature by much more than these hot metals. So these hot metals are going to just barely heat up the water, but the aluminum by more because it absorbed more heat to begin with. Okay, so that'll take us through this recitation activity. Good luck this week, and this is the last activity before midterm 2. So good luck on midterm 2.